So this is part 2 of the lecture. We left off with focusing on the transition metals and knowing the location of the lanthanides and the actinides, and knowing that the actinides, these intertransition metals, are radioactive. But that's about all we're going to cover for this, for these metals. So chemical formulas. When we have an element, we can use the chemical symbol. When we have multiple elements together and they form a compound or a molecule, we use a chemical formula. Now, instead of writing out all the name, we use their chemical symbols. They indicate which atoms are found in the molecule and in what proportions they are found. So it's important to pay attention to charges and paying attention to subscripts. So subscripts are given after the chemical symbol to represent the relative number of each atoms. So iron 2, O3, or oxygen 3, means that there are 2 iron atoms for every 3 oxygen atoms. So this is different. Okay, this ratio is different than the law of definite proportions. Okay, this is talking about atoms, not by mass. But this means there are 2 irons to 3 oxygens. And we use the chemical formulas to help with describing what's happening in a chemical reaction. So in the case of when we have hydrogen and oxygen. Now in nature, hydrogen and oxygen are what we call diatomics, which means you're not going to find a hydrogen by itself. It's always going to be bonded to a second hydrogen, just like oxygen. But when these two interact, what's going to happen is one of the oxygens is going to interact with 2 of the hydrogens to form water. Now, we represent chemical formulas for elements and compounds, but there are multiple types of compounds. So free elements are just elements not combined with anything. So these would just be the chemical symbol found from the periodic table. So sodium, potassium. And remember we talked about from chapter 0 that sometimes their chemical symbol does not necessarily overlap with the name. So sodium is actually from a, I think Greek or Latin word, natrium, or natrium. Potassium and things like that. Now, there are non-metal molecular compounds and ionic. You might have seen, if you've taken chemistry several years ago, that instead of calling it a non-metal molecular compound, it also can be referred to as a covalent compound. And this talks about the kind of bonding. And we'll learn about this in later chapters, but just for a brief introduction, there are 2 main types of bonding that we're going to talk about in this course, and that is covalent and ionic. Covalent is between 2 nonmetals. So once you know and memorize the location of the nonmetals and metals, it'll help you identify what kind of bonding and what kind of compound you have. Ionic is between a metal and a non-metal. So that would be something from the left side with something from the right side, where the non-metals are just on the right side of the periodic table. The other type of compounds are acids and diatomic molecules. We will also be discussing hydrates. And this is particularly important for lab. So each type of compound can be represented by a chemical symbol or chemical formula, but also by a name. And some molecules have a common name. So in this case, water. It's not very descriptive of the compound, but it is a common name that almost anyone, even without a chemistry degree, can know that water is H2O. Some names for chemical formulas are more descriptive, such as hydrofluoric. So hydro, you can think of hydrogen, and fluoric sounds a lot like fluorine, so you know that there's a hydrogen and a fluorine. The acid portion lets you know that this this compound is found in water, so it's not by itself. So this means that there's a hydrogen and a fluorine in solution, so hydrofluoric acid. If you have gaseous form of HF, it would just be hydrogen fluoride. Now, as we go along in this class, we will be talking about different naming systems. And some of the namings will get more specific in further chapters. So we do have an acid and base chapter. However, for safety in lab and just to get you started, please know the name and the formula for these 4 acids. They're important for, some of them are important for lab, but also you might find this on the homework, and I just want you to be familiar with the name. Now again, this acid term means it's in solution, okay? And so unless it tells you that it's aqueous or in solution, you would name it just like any other formula. And we will talk about naming formulas in the next few slides or on Wednesday. Now we talked about diatomics a little bit. I gave you a brief introduction. So if we break down the word, di means 2, atomic means atoms. So this means there's a combination of 2 atoms. Now they do not have to be the same element, such as hydrofluoric or hydrogen fluoride, or hydrochloric acid, which is a hydrogen and chloride. There are some diatomics that form naturally, and there are 7 in particular that you will need to know and be familiar with. And here's the 7, and it even forms a nice 7 here. So hydrogen, nitrogen, oxygen, fluorine, and then most of the halogens. So again, diatomic means 2 atoms. Triatomic would mean 3. These molecules would behave very differently, O2 versus O3, or ozone. Now, when we speak of these elemental forms of these substances, of these 7 elements, we mean the diatomic unless expressly stated. So when I say hydrogen interacts with oxygen, your first instinct should be, oh, that's H2 interacting with O2. So learning how to write the formula is an important step. The first thing to know is the chemical symbol, as indicated by the periodic table, has 2 different options. If there is one letter, it is capitalized. However, such things like chlorine, the first letter is capitalized and the second letter is lowercase. We typically go from left to right in the periodic table. So hydrogen is toward the left of oxygen, so you have hydrogen before oxygen. It also indicates how many atoms are bonded to, are interacting in the compound. So in this case, there's 2 hydrogens for 1 oxygen. there's 2 oxygen for 1 carbon in this case. Here, for every 1 carbon, there's 4 hydrogen, and so forth. When you see the elements are in their actual numbers and cannot be reduced down, we call that a molecular formula. And in this class we'll cover 2 main formulas, molecular formula and empirical. So molecular formulas is typically used for molecular compounds. Empirical formulas are used for ionic compounds, but can be used to give the lowest whole number ratio of atoms in a molecule. So in this case, I've listed some molecular compounds. And notice that some of these can be reduced down further. Now, in many cases, the molecular formula is equal to the empirical formula, such as a case if the chemical formula cannot be reduced down. But here you see H2O2. Both of these values can be reduced down to 1, and so the empirical formula will be just HO. Here, for methane, 1 and 4 does not reduce further, so the empirical and the molecular formula are the same. Here, 2, 6 can be reduced further, so you get CH3O. And HF is already at the lowest ratio, so it remains the same. So that is how you write the chemical formulas. And we'll worry about naming soon. But when we talk about elements, we have to worry about how to write them, but also how to draw them. And in your homework, you might see chemicals and compounds drawn in several different ways. So if you see just the letters written out in these stick forms, this is called structural drawings. Now you might see it as a planar molecule, or you might see it where it tries to give you some dimension, and this is called a perspective drawing. And in class, when we get to chapters 8 and 9, we'll learn how to draw structurally. However, you'll see sometimes in your book, you see prettier models. And there are 2 types of models that deals with more of the 3D aspects. But both of them use the similar color coding and size. So you see that in almost every model, carbon is represented by a black sphere, hydrogen is white, and oxygen is red. However, some models represent the bonds, and this is called the ball and stick model. You see you have balls, and then the bonds are sticks. There's a second type that you might be familiar with from the homework or from the book, and that's called the space filling model. And this just kind of gives an idea of how much space in the 3D sphere that is being taken account, or how much these molecules can overlap. So the bonds are not as prevalent, but you can see that there's a carbon interacting with an oxygen, and there's a nitrogen represented by blue with hydrogens.